Welcome. This section is called Measures of Variation or Dispersion. So quantitative variables are often summarized using numbers to communicate their spread or dispersion as well as their center. So previously we talked about a measure of central tendency in a data set, and now we'll talk about spread. So the first measure of variation or dispersion is the range. We've seen this before, and it's quite simple. The range is just the highest value in the data set minus the lowest. So it only involves those two extreme values. So we won't be using range very often. We're going to move on to studying two other measures of variation called the variance and standard deviation. And these will involve a calculation that includes all numbers in a data set. And it tells a researcher how tightly the data values are clustered around the group mean. So we're going to dive into an example, and I'm going to develop this formula for you, which might look a little complicated right now, but we'll break it down. So the sample variance of a data set is what we'll do first, and then I'll continue with the other measures listed, but let's dive in. So 3 factories make chocolate chip cookies. A random sample of cookies is taken from each factory, and the chip counts are recorded. All right, so let's start with factory number 1. All right, so there's 5 cookies there. So we're talking about sample data. So our sample size here, lowercase n, is 5. So the first cookie had 7 chocolate chips, the next had 8 chocolate chips, etc. And what I'm going to do is list those data values in the table. So X will represent the number of chocolate chips in a cookie. So we had 7, 8, 8, 8, and 9. And I'm going to add, so capital sigma, those X values. I'll go ahead and do it on the calculator here. So if I add all of the chocolate chips in total, that would be 40. And then we'll go ahead and find the mean of the sample. So the symbol is X bar for sample mean. And the formula was adding the data divided by number of values. So 40 divided by the 5. So we're averaging for that sample 8 chips per cookie. All right. So I'm going to compare that sample to the sample from factory number 2. So factory number 2, we have 5 cookies, so n is 5. And I'll go ahead and now write those values in the table. So these were 4, 5, 8, 11, 12. And if you'd like to check, when you add those values, you're going to again get 40. So if I put all the chocolate chips together, there'd be 40 chocolate chips. So the sample mean, even though the data is quite different than factory 1, we're still going to end up having 40 divided by 5 or 8 chips. So the means are the same, but what we're trying to measure is variation in the data. So just looking at it subjectively, these cookies tend to show more variation than those cookies. And in particular, we're going to compare cookies to the mean of the group from which they were drawn. So let's go with factory 1. All right, so the mean for factory 1 was 8. So X bar, we're just going to write it down the page so we can do some comparing of each cookie with that group mean. So it's called the deviation from the mean. We'll take each cookie and see how much it differs from the average of that group. All right, so if you got the cookie with 7 chocolate chips and we compare it to the average, how much it deviates or differs. So I'm going to get -1. So the negative is indicating that that cookie is 1 chocolate chip lower than the average cookie. If you got a cookie with 8 chocolate chips and the average of that group was 8, then your cookie doesn't deviate at all from the mean. All right, so just continuing this process. And then finally at the bottom, if I get the cookie with 9 chocolate chips, 9 minus 8 is positive 1. So that cookie had 1 chocolate chip more than the average cookie. So I'm just going to write the units up here. So we're measuring the difference in chips for each cookie compared to the average. Now, if I add that column, so if I sigma add the values of each of the x minus x bar, the deviations from the means, if we add that column, you'll see here that -1 and 1 cancel out to 0, and then we have zeros. So when we add that column, we get 0. Okay, so next step. Every data set that we work with, when we add that column, we always get 0. So that's not helpful in helping us determine that one data set varies more than another. And that is why we move on to the next calculation called the squared deviation from the mean. So I need to find a way that we don't always get 0 for every problem. So if we take our x minus x bar, those are our deviations from the mean. If we square those numbers, we're going to eliminate negatives. So for example, the -1 for that first cookie, if we square it, -1 times -1. So a negative times a negative is a positive. All right, and then 0 squared, of course, is 0. So we're just squaring the values from the previous column. And then at the bottom here, 1 squared is 1. All right, so if I add the squared deviations from the mean, now I'm going to get 2. All right. So the idea is we're going to look at that number 2 in comparison to that same value for factory number 2. All right, so factory number 2, the sample mean x bar, that was still 8. So those values were the same for both factories. But now what we're going to see is deviations from the mean. We'll start to see in general bigger deviations. So the cookie with 4 chocolate chips, if you compare it to an average cookie, that's -4. So that's 4 chips below average. 5 chocolate chips compared to the average, that cookie, -3, so 3 chips below average. Now the next cookie does have 8 chips, so there's no deviation from the mean there. And then the 11 chocolate chips minus the average, +3, so that cookie is 3 chocolate chips above average. And then finally 12 minus 8, that cookie is 4 chocolate chips above average. So if we add the deviations from the mean for each of those cookies, so what you're going to see here is my -4 and 4 would cancel, -3 and 3 would cancel. So adding up all those values, we again get 0. So that column for every data set would be 0. So it's not helpful in terms of comparing data sets. And that's why we move on to squared deviations. So x minus x bar deviations, and then we square those values. So if I take -4 and square it, negative times a negative is a positive, and 4 times 4 is 16. -3 squared would be +9. 0 squared, of course, is 0. 3 squared is 9, and 4 squared is 16. So if I add the squared deviations for each cookie, so I'll come over to my calculator here, make sure we don't mess up. 16 plus 9 plus 0 plus 9 plus 16. So now that total is 50. All right. So all we're trying to do right now is a little bit of comparing. So that total is bigger than that total. So in general, telling me that this factory shows more deviation from the average among its cookies than that factory. Okay, so those values, the 2 and the 50, I'm going to come up to the formulas. What we're trying to do here is develop a formula for sample variance. So the variance of a data set. The symbol for it is S squared, and the numerator is the column values that we just found. So we just did a bit of work to figure out what that numerator is, and then we're going to divide that by the sample size minus 1, and that's called our sample variance. So let's do that next. All right, so sample variance. So the symbol for it is S squared because it was developed by squaring values. Now we already got that numerator, so I'm just going to write that 2. So that 2 is the numerator. And then we divide by n minus 1. So I'll just write n minus 1 first, and then we'll substitute. All right, so 2 over. So our n, our sample size was 5, so 5 minus 1. So in this case, 2 divided by 4, and that will be 0.5. Now let's talk units for a second. So the deviations from the mean were how many chips a cookie differed from the mean. But when we squared those numbers, the units get kind of weird here because you would talk about squaring chocolate chips. So the units would be chips squared, which is just kind of silly. You can't really think about a square chocolate chip. So we don't use this value very often because the units don't match the units of the data. But that is called the sample variance. So what we usually do is move on to what's called the sample standard deviation. So the standard deviation of a data set is just the S. So the standard deviation is just the square root of the value we got for the variance. So by taking the square root of S squared, that gets us our S. So we have our S squared. That was 0.5. All right. So by taking the square root of that value, we're going to get rid of that square and we'll go back to just units of chips. So let's do that. So on our calculators here, square root is above your x squared button. So second square root, we'll type in the 0.5. And now we will have to round this. So I'm going to just round it to 1 decimal place. And that's going to be 0.7. So the standard deviation of this sample is 0.7 chips. All right, so we're just trying to get a feel for the difference in variation between the sets. So right now it's kind of hard to interpret exactly what that's telling us on its own. What we want to do is see how it compares to the second factory. All right, so let's start with sample variance. So S squared. So the numerator is going to be that sum of the squared deviations. So that's 50. So we're just finding that value from our table. And then it's divided by n minus 1. So in this case, again, n was 5 cookies. So 5 minus 1. So 50 over 4. So 50 divided by 4 is 12.5. I'm not going to write units now that we've had that discussion. We'll just move forward here. All right, that's called the sample variance. Sample standard deviation is S. So standard deviation. So I'm just going to point out here that SD is just an abbreviation for standard deviation. That's not a new symbol. It's just so I can save a little space. So that's just an abbreviation. The symbol for standard deviation of the sample is S. And it's the square root of, and I'll write it in English this time, it's the square root of that value called the variance. So variance was our S squared value. So square root of 12.5. And again, we'll have to round this, but coming to the calculator, square root of 12.5 is 3.5. All right, now I will write units. So that's going to be what we usually work with, the standard deviation, because the units match the original data. Okay. So again, all we want to do right now is a little comparison and what it tells us in terms of the size of these values. So the standard deviation of factory 2 was 3.5 chips. The standard deviation of factory 1 was 0.7 chips. So they both had the same mean, but now I'm seeing more deviation from that group mean for factory 2, because that's the higher standard deviation as opposed to factory 1. So we are not going to have to calculate standard deviation by hand. This was just to demonstrate. We are going to go ahead and use technology and our calculators, but trying to get a feel for what we're measuring here when we discuss standard deviation throughout the semester. So how much the data differs from the group mean. All right, so the larger the standard deviation, the more deviation we're seeing from that group mean. Now let's do one last factory. So what if we have a third factory and every single cookie sampled here had exactly 8 chocolate chips? So rather than creating a whole new table, I'll just focus here on an 8. So if all values in the table were 8, and the mean of that sample, of course, would be 8 because they're all 8s. So every single cookie here would be an average cookie. So when all data values are the same, then the standard deviation of that data set, in this case, a sample, so S, there is no deviation. So our standard deviation would be 0. All right. So that is how to calculate standard deviation by hand. But again, we are going to focus on using technology now. So we won't have to do that by hand each time. It can be a little cumbersome and a bit tedious. So let me just go down to our calculator approach. But before that, let me just talk symbols again. So sample variance is S squared. Sample standard deviation is just S, square root of the variance. Now, if instead of sample data, we actually had population data, we switch symbols and the formula changes a little bit. So first, let's talk about symbol, and that guy there is a lowercase Greek sigma. So that's what a sigma looks like, and I'll write it below as well in a moment. So that's sigma. So variance is sigma squared, like S squared, but for population, sigma squared. And in the calculation, if we were to create the table and go through the whole thing again, the calculation changes just a little bit. The numerator wouldn't change. We're going to compare every cookie to the average cookie, mu, so the population mean. And the denominator is going to be population size n. So the difference here is that it's n minus 1, sample size minus 1 for the sample variance, but population variance, the formula changes just a little bit. So again, we'll have our calculator help us out to find those values for our standard deviation. All right, so let's try it. All right, so I have a random sample of 6 churros and the calories are recorded. So if you want to get that in your calculator, so stat edit, and I've already entered that. So if you wanted to pause and enter your data, that would be the first step. And then we are going to do stat. So stat button, calculate, and then the first choice there, 1-var stats. And if our data is in L1, we could just hit enter. L1 is the default. And then your screen should match the output here I showed in the notes. So the point here is to let the calculator do some work for us, and then we have to focus on symbols. All right, so let's start with the statistics. So because it was a sample, these measurements are called statistics. So sample size is lowercase n, and there were 6 churros. Sample mean is x bar, and then I can see that that came out to be 301.5. So the average calories, 301.5 for the sample. And then we're not going to use variance really at all for quite a long time. So we tend to focus on standard deviation. So sample standard deviation, and this one we will have to round. So we'll do 1 decimal place, and you'll see S. You'll see an X next to it to stand for the variable. We do not have to write the X. We'll usually just write S, and S is 21.3. So both of these would have units of calories, so we won't keep writing units all the time, but they would both have units of calories. And then the comparison here is, what if, number 2, we had an order of churros and it contained 6 churros, and the calories here in each are recorded. All right, so I apologize. My notes here got cut off. I might be able to get them on the page without starting my lecture all over. There we go. Oh, I had it. Hold on. All right, always hate when this happens. While I got so far through this video. There we go. Okay. Almost. Yeah, we're good. All right. So I have a population of churros. So no sampling is mentioned. It's the entire order has 6 churros, but the data here is exactly the same. So the key is to understand that populations are described by parameters, and we switch symbols. So I know my values here got cut off. I'm just going to rewrite them real quick. So for samples, it was lowercase n was 6. The mean, x bar, is the sample mean. And then sample standard deviation is S. All right, but if it had been a population, then the population size is capital N. And you'll see here on the calculator, it wrote lowercase n. So the calculator can't read a question for us. It's not going to be able to tell us if we're dealing with a sample or a population. So we have to do this ourselves. So the population mean, so the formula for finding a mean is the same for any data set. You add up the data and divide by, in this case, 6 churros. So the math doesn't change when you're finding a mean. So numerically, the answer is 301.5, but we can't use X bar because the symbol for population mean is our mu. So we need to know that ourselves, but then we can grab the numerical answer from the calculator. Now, population standard deviation is our lowercase Greek sigma. So it looks like that. Something close to that is fine. Now, here's the deal with standard deviation then. The formula for sample standard deviation is a little different than the formula for population standard deviation. So numerically, the answers will be different. So sigma, you'll see there on the calculator, is 19.5. We'll round to 1 decimal again, 19.5. All right. So this is how we're going to find standard deviation now for the rest of the semester. We will not do a by hand calculation. We'll do 1-var stats. And then we need to focus on the symbols because the calculator doesn't know that. So sample mean, population mean, the numerical answers are the same, but the symbols are different. For standard deviation, the sample standard deviation and the population standard deviation have different symbols, and as well, they have different numerical values. All right. And then we will move on and take a look at how to apply these values, the mean and the standard deviation, to some problems.